All right. Well, happy Friday.
Yay.
So into week 4. We're moving along quickly. So I have a bunch of grading to do this weekend, 215 and 222. So I'll try to get your stuff graded sometime this weekend, but it'll be probably later, towards Sunday maybe. And then Monday we can talk about details of PA2. I can show you some code. It's not very different from PA1. Any questions up to here? Stuff you're dying to understand. All right, well, let's talk about PA3. So PA3 is posted. And as promised, this is about stacks and queues. And you're going to implement these structures using linked lists. So you can reuse some of PA2.
We are talking about dynamically linked lists.
Yes, so we're really never going to use arrays for linked lists again. That was purely a learning exercise. So yeah, we want to use dynamic memory, mallocs, and all that kind of stuff. So the main program for PA3 is a little different feeling from the main programs we've used so far, because we're dealing with two structures here, a stack and a queue, and they're totally separate from each other. And the program that you're going to write, the main program, basically lets the user interact with these structures. So you can say, I want to insert this into the queue, I want to remove what's at the head of the queue, I want to push something onto the stack, and so on. But the program itself has a notion of state. It has two modes that it can be in. It can at any time be in either stack mode or in queue mode. If it's in stack mode and I say add the number 15 to my structure, it'll add 15 to the stack. If I'm in queue mode and I say add 15, it'll add it to the queue. Okay, so we have one set of commands for adding something and removing something, but where it puts those or takes them from depends on what mode we're in. So the program has two modes. It can be in stack mode and queue mode. So your first two commands, S and Q, basically do two things. One, they control what mode you're in, but they're also used to print the structure. So if the user types the command S, you should do the following two things. One, print the contents of the stack, and then two, set your mode to stack mode. If you're already in stack mode, then S is just a print command, right? It just prints the contents of the stack. But if you were in queue mode, update something to say, okay, I'm in stack mode now. Queue does the same thing, prints the contents of the queue, and then make sure your mode is queue mode. And you stay in that mode until the person changes the mode. And whichever mode you're in, if the user types an integer, you should add it to the structure. So if you're in stack mode and the person types 25, enter, push 25 on the stack. If you're in queue mode and the person types 25, enter, insert 25 to the tail of the queue. And then the P command is used to either pop the top of the stack or remove from the head of the queue. You should remove it from the structure and then print it out so the user can see it. And then the Q command exits the program. All right, when you print the stack or the queue, I want you to print the contents on one line separated by spaces. For a stack, I want the top of the stack on the left, followed by all the entries. For the queue, I want the head of the queue on the left, all the entries, and then the tail on the right. And when you exit your program, all memory that you've allocated should be freed. So when you remove, you want to free stuff right away, and when you exit, you want to go through some kind of routine to clean up all the structures. And I mentioned here you should start in stack mode. I added that like 30 seconds after I posted the assignment originally, so If you got the very first version, it doesn't say that. So start in stack mode. All right, so on Canvas, I also posted a link. Well, not a link, but I mentioned that there's sample code available on the server. Man, I love that. So under /temp, there's a file called PA3 sample. It's an executable version of what PA3 should do. So if you're not sure what Q and S do, right, you can run this and see what kind of behavior I'm expecting. So temp PA3 sample, there's the list of valid commands. So I'm going to go into stack mode, and it tells me my stack is empty. Okay, there's nothing to print. I'm going to push the numbers 10, 20, and 30. And now if I look at my stack, top of the stack is 30. It's the last thing I pushed. Followed by a 20, followed by a 10. Yes?
How specific do you want us to be with the formatting? Because on PA1 and 2, you just want us to prompt. Do you want us to label stuff? Or
As long as it's one line and it doesn't take up the whole line, if you want to use a % sign or something, that's fine. But I don't want to see like this every time I type a command, right? So I want it to be pretty clean. So if I'm just inserting, I'm just inserting, and so on. Okay, so I got 3 things on the stack. If I say P, it should pop the top of the stack. That's going to pop off the 30. And now if I say show me the stack, it's just got a 20 and a 10. And now if I push on a 40, my stack looks like that. 40, 20, 10. 40 is at the top of the stack. If I try to remove, top of the stack is 40, and then 20, and then 10, and now my stack is empty. If I try to remove again, it tells me the stack is empty. It's an underflow. And I can put more things on the stack, and so on and so forth. Okay, if I type the letter Q, I'm going to go into Q mode. My Q is originally empty. If I type S, I come back into stack mode. My stack is still there. Okay, don't get rid of your stack just because the user's going into Q mode. Okay, so I'm back in Q mode. Let's add a 1, 2, 3, 4, 5, and look at the Q. Head of the Q is 1. That's the first thing I added. So if I say pop, it's going to remove that first thing at the head, which is a 1. So print the head of the Q, and now my Q has 2, 3, 4, 5. If I remove the next thing from the Q, that's a 2, and now my Q is just 3, 4, 5. If I go back to my stack hasn't changed. Stack never changes when you're in Q mode. The Q never changes when you're in stack mode. Okay. So here if I say print the top of the stack, it's going to give me my 5. And if I print again, it's going to give me my 4, and my stack has 3, 2, 1. My Q has 3, 4, 5. Okay. Keep these totally separate from each other. If you go into your Q and you remove the 3 and the 4 and the 5, right, your Q is empty. If you try to remove something else, just print a message saying the Q is empty. You can't remove. Don't corrupt anything. Don't exit. Don't crash the computer. Don't delete your Sentinel node or do something crazy like that, right? It's just a user error. You can't remove from an empty queue. Just tell them Q is empty. But everything should still be fine. The stack is still unharmed. And I can go back to inserting things into my queue. You can just go back and forth all day, right? And then when you're done with everything, uppercase Q gets you out, and it should free all memory. So clear what the behavior is, the intended behavior? All right, so details, you're going to implement these with linked lists. And I would like you to do the following. For the stack, linked list, first node is your Sentinel. The node after the Sentinel, that's always what we consider to be the top of the stack. So when you push into the stack, what you want to do, let's say push n, you want to create a new node with n. You want to have that point to the old top of the stack and have the sentinel point to your new node. And now this is the top of the stack. So you basically insert in the beginning of the list. And that's just your add function from PA2, but instead of searching to find the right place to add, you just add right after the sentinel. And then when you want to remove, what do? Just return the node right after the sentinel. So start at your sentinel, that points to this node. This is the node that I'm going to want to return the value of that. So change the sentinel to point where this node is pointing. Free this from memory with a call to free, and then return the value n. Print it out. So you're just removing the first node from the list. So it's a simplified version of your delete function, where instead of finding the node to delete, you just delete the thing right after the sentinel. And that's have the sentinel point where that first node points, but free your memory. All right, so the stack implementation is really a subset of what you've already done. The queue will be a little different. So there's your sentinel. Here's your linked list. So the node right after the sentinel, that's the head of the queue. The node at the very end, that's the tail of the queue. All right, which end do we insert in? Tail. Good, thanks. So if you want to remove something from the queue, that's just the first node. It's just like popping the stack, right? Take whatever the sentinel points to, have it point where that node points instead, return the value from that node, free it from memory. So removing from the queue is same operations as popping from the stack. Inserting in the queue, slightly different. You have to start at the sentinel, go all the way through till you get to the tail, which points to null. Make yourself a new node. With n, have your tail point to that new node. Now our tail is down here. So it's like add for the stack, but instead of adding the beginning, you just add at the very end. So pushing is like the thing you do before your for loop, and inserting in the queue is like what you do after the while loop in your add function, when you say, oh, nowhere to put it but the end. Don't feel like you're bound to your PA2 code though, right? It's actually probably more instructive to kind of do some rewriting. One, because PA2 is the culmination of probably a couple of weeks of effort, and in some cases, when we write code like this while we're simultaneously trying to learn these concepts, our code can end up with all these different like branches to it, right? Where we're done and our code may be this big long thing where we're doing a bunch of stuff, and if we went back to rewrite it now, we might say, oh, I can do that in 3 lines, right? But we may have done 5 things and then done 3 other things to undo those, and so on and so forth. So rewriting is a nice way to sort of, it's like rewriting your notes basically. Right, it lets you take the more clear concepts and practice with those. And you know, it's not exactly PA2 either. It's, you know, always happening at the beginning or the end of the structure. So don't feel like you're bound to them. Don't feel like you have to be elegant either. I've had students, when I've given this assignment in the past, who try to make one uber list function that they pass a parameter to, and it does all of these things in one function based on some value that you pass to it, right? That's kind of nice, that's kind of slick, but it's confusing, and I've seen people get really tripped up by trying to make that work. There's nothing wrong with writing 4 list functions. One to insert in the beginning for a stack, one to remove from the beginning for a stack, one to insert in the beginning for a queue, one to remove, or insert at the end and remove from the beginning for a queue. Right? Code is cheap, memory is cheap, especially today. Right? Your time is precious. your clarity of thought is priceless. So if you want to spend extra space in your code to make it a clear presentation of what's going on in your brain, do that. Right? Don't feel like you have to somehow make it concise or right or something like that. Ideally, when you finish your code and you look at it, it should give you a good feeling, as opposed to, you know, oh my God, I hope nothing goes wrong. So that's the goal. All right, so that's what's in the details section. Notes, the only way you'll run out of memory is if the system runs out of memory. It's not likely to happen, but as usual, when you call malloc, check the return value, make sure it's not null. That's just a habit you want to get into. Otherwise, you have production code, and one day it seg faults, and nobody knows what to do. So anytime you call malloc, check the return value. Make sure it's not null. That's the only memory potential issue. Free all your memory at the end. Okay, test your code thoroughly. Someone started a discussion for PA2 on ways to test code. They started it kind of towards the due date, so there wasn't a lot of discussion. But you know, I'm totally happy to have these kinds of discussions going on in Canvas. Hey, I tried these things. Can somebody think of other things I should check? Right? That's a good kind of groupthink exercise. So test your code. Lots of comments, right? A make file, please. And in this case, I want you to call the executable program PA3. Okay, so instead of main or program or whatever, try to call it just PA3. So that after you say make, enter, you can say PA3, enter, and it runs your program. Okay, so it's just what you name it in the target make file line. And then wrap it up in a tar file, submit it to Canvas 2 weeks from today. Minus 3 hours, 20 minutes. All right, clear enough? So let me mention one detail. If you get bored, if you blow through this afternoon and now you got 2 weeks with nothing to do for 222, or you know, if you have a few days left at the end, think about this. With the queue, when we want to insert, we have to insert at the tail. We've got to start at the sentinel and follow this whole chain of nodes until we get to the tail. If we've got 1 million nodes, that's an expensive operation. Okay? There are ways to avoid that and make inserting order 1. And one way to do that, of course, is just a doubly linked list, right, with a circular structure, so from the head we can go back to the tail. That'll totally work, and if you want to try that, go for it, right? You should be getting more and more proficient at working in a Unix environment, so you should be able to do something like take your program that works well, make a new directory, copy all your code over, and start working in that new directory, right? If you're using Git and you know how to make branches, you can do it that way. But, you know, simplest case, just make different directories to work on different versions of your code. Make a version where you try using a circular doubly linked list, right? And if it doesn't work, your old code is still unharmed, right? It hasn't changed at all, and maybe you've already turned it in, you know. But projects I'm working on, I mean, I'll end up with 20 or 30 different versions of my code in different directories, and I'll throw a README in each one to remind me what I'm doing in there. And it's just disk space, you know. It's not a huge deal. So another way to handle this efficiency is to note that when we're removing, we're just coming from the head. That's easy because the sentinel points to it. When we insert, we just need to get to the tail. Once we're at the tail, all we need to do is change this, so instead of pointing to null, it points to our new node. So if we have a way to get to this node quickly, we can do this in order 1. So we can have a variable called tail pointer, which points to the tail. And when we want to add something to the tail, what do? We follow tail pointer, it points right here. We make our new node. We have our thing the tail pointer is pointing to, instead of going to null, point to our new node. And then all we got to do is set tail pointer equal to our new node. So now it points there. And we've totally updated the system. And each of those is an order 1 operation. There's no searching involved. So what is tail pointer? Well, it's a struct node star. You could make an evil global, but you could also modify the structure of these nodes to leave space for a tail pointer in the sentinel. Or if you're really edgy, maybe you could use the data field in the sentinel node, but I wouldn't do that because it's not as big. But you could do something like that, right? But you could define a structure which just looks like a number and a next, and then just call this spare and have this be a struct node star. And don't use it for anything except in the sentinel. In the sentinel, you can make this your tail pointer. And now the tail pointer is part of the sentinel node, which is the thing you're using to manipulate the list. It's what you pass to a function and so on and so forth.
But if you have like n number of nodes, isn't that going to take a lot of space for that spare?
Yeah, it takes 50% more space. So yeah, that's a good chunk of space, but memory is also cheap,
Okay.
right? Not if you're going to do a trillion nodes. Then it's definitely not cheap. For us, though, that's fine. It's a good compromise. There's kind of a general trade-off in a lot of programming between space and time. We can sometimes do things with less time, but it takes more space. This is a classic example. We can try to conserve space and take more time. And that's a whole series of lectures we could go into another day, another course. But there seems to be some kind of almost a Heisenbergian connection between the space and time where you can reduce one but the other one goes up, and it's hard to bring them both down all the way. But this is kind of like parallelism in a computer also. We can have lots of processors and do a problem quickly, or we can have a single processor which takes less hardware but it takes longer to run a process because you have to do everything on one CPU. Anyway, that's going to turn into a big sidetrack if I'm not careful. All right, so good on this? Okay, awesome. So PA3 sample /temp, I mentioned that on Canvas, so if you want to explore that. All right, well, wrapping up stacks and queues. We started off with some kind of like hand-wavy motivations for why we use queues when we're buying groceries, or stacks when we're doing homework and the phone rings and so on. But let's look at some algorithms for solving problems that are related to stacks and queues. So there's a famous problem called the n queens problem. So how many people here have played chess? That's so cool. I had no idea that yeah? I had no idea people still played chess. That's awesome. So as you know, the queen is a very powerful piece and can move in pretty much any direction. Can't do what the horse does for some reason, but can do what bishops and rooks do. So 8x8 board, and if we place a queen at, say, this position right here, it can attack anything in this row, anything in the same column, or anything along the diagonals that it's sitting on. So queen generally has 4 paths of attack, and any piece anywhere along those paths can be captured by the queen. The queen does all the work, and the king just kind of sits back and gets protected. I never figured that out. So a question is, if you have 2 queens, can you place them on the board in such a way that they don't attack each other?
Yeah.
And you can, right? If we put one queen right here, we could put another queen up there, and if you figure out the attack paths, they don't intersect. Right? So those 2 queens won't attack each other. And certainly, since this board is 8x8, if we have 9 queens, we cannot place them on the board in a way that they don't attack each other. And we can see that if you've done 215 already, pigeonhole principle. because there's 8 columns. If we have 9 queens and we place them each in some column, at least one column will have at least 2 queens. And 2 queens in the same column, they can attack each other. But pigeonhole principle doesn't tell us that 8 is possible or impossible. And in fact, you can put 8 queens on a board and they won't attack each other. So the n queens problem is, how do you place n queens on a board so they don't attack? So for an 8 by 8 board, we want to look at this question of placing 8 queens in such a way that none of them can attack the others. And let me propose an algorithm. So I'm going to number these squares. So 64 squares, we'll just number them from 1 through 64. And here's a really naive way to go about solving this problem. We're going to take our first queen, we're going to place her on square 1. We're going to take the second queen, place her on square 1. Third queen on square 1, place all the queens on square 1. And then we're going to hand this to some judge and say, have I solved the problem? And they're going to say, no, you can't have 2 queens in the same square. Okay, so we'll take that last queen that we placed and move it to square 2. And we'll say, have we solved the problem? And they'll say, no, you've got 7 queens on the same square, right? So we have this judge that can look at the board and the placement of queens and tell us whether it's a solution to the n queens problem or not. And those first few solutions, we're going to have all the queens stacked up. But eventually we'll start spreading these out. And we'll get to a place where we have 8 queens all sitting in positions 1 through 8. And we'll say, is that a solution? No, they can attack each other. Okay, so we'll take, let me draw these on the side so I don't overwrite my numbers. But these are actually in. Okay, we're going to take this queen from the 8th square and we're going to move it to the 9th square. And we'll say, is that a solution? No. And we'll try the 10th and the 11th and so on. And none of these are going to be solutions because all of these are attacking each other. But eventually, we'll put our 8th queen down here in position 64. That's still not a solution. So we'll take that queen, try to move it to somewhere else where there's nowhere else for it to move, right? So that tells us we've got to go back to the rest of this solution and change something. Well, we can do the exact same thing. Take the 7th queen and move that. And so we can work through this process, and we wouldn't do this as people because we know right away none of this is going to get us a solution until we put these things in different rows. But if we're very kind of naive like a computer is, right, we could work through this methodically, systematically. And at some point, you know, we may have moved the first, the last 3 queens here and tried this solution, and we're told that's not a solution. And so we're going to go back and we're going to move this 5th queen down here. And what we're doing here is really a search problem. We're trying to enumerate all the possible ways that we can place 8 queens on this board, whether or not they're attacking each other, whether or not they're in the same square. We're just trying to come up with all the possibilities one by one and check them to see if they solve the problem. And if we find one that solves it, we're done. So we can use a stack to do this inside a program. And here would be the idea. So here's our stack. And I'm going to envision this stack as things kind of coming in from the bottom. So this is going to be where the first thing gets put on a stack. The second thing I'm going to draw below it, the third thing below it, right? So top of the stack is going to be down here at the bottom of the page. Okay. So I'm going to start off and I'm going to place all the queens in position 1. So first queen goes in position 1, second in 1, and so on. And that's what my stack looks like. This shows me the position of the 8 queens. And those 8 numbers, I can pass that to my judge program and say, okay, is this a solution? And it comes back and says no. Okay, what do? I'm going to pop this first 1, I'm going to increment it to a 2, I'm going to push it back on the stack. And now I'm going to pass this to the judge. Now the solution, I'll pop that, increment it, push it back. I'll do that all the way until it's a 64. Pop that off, increment it. Incrementing it gives me a 65. Okay, that's not a valid position. So instead of pushing 65 on, I'm going to go back and I'm going to pop the stack again. Increment that, push that back on. And then I'm going to push 1s until my stack is full, or until I've got 8 things on there. So now I've got a solution where I've got 7 queens on here, but I took that 7th queen and I moved it to position 2. And that's not a solution, so I'll try 2 and 3 and 4 and so on all the way up to 64. And then when I pop that off, I'll increment 65, that's too big, so I'll pop the stack again, increment, push back, and then push on some 1s. Okay, this is going to go on until we've got a 64 in that 7th position. This comes down to a 64. We pop it, we get 65. That's too big. So instead of pushing it, we'll go to the previous one, pop it, increment. That's 65, that's too big. So we're going to go back, pop again, increment. That's a 2, push the 2 on, and then push 2 1s. And if you ignore the fact that we're looking at silly possible solutions that we know aren't solutions, right? What we're doing is taking every possible placement of these 8 queens. And eventually our stack will look like this. And we'll pop this, add 1 is 65, that's too big, so pop this, that's a 65, and so on. Pop this, that's a 65, too big, so pop this, increment, push it back, there's a 2. We've just moved that first queen from the first position to the second. And then push back some 1s. And after that process repeats a total of 64 times, our stack will look like this. We'll pop, add 1, 65, no good. Pop, add 1, 65, no good. We'll keep doing that. We'll pop this entry, add 1, get 65, that's no good. We'll try to pop again. We'll realize the stack is empty. Our algorithm is finished. Okay, that's an extremely systematic way to traverse this search space of possible placements of 8 queens. It does a lot of kind of boneheaded things like letting queens sit in the same square, or thinking that somehow having queen 1 over here and queen 2 here is different from having queen 1 there and queen 2 there. It thinks these queens are individuals, right? But ignoring the inefficiency of that, right? This is very easy to implement if you have a stack, right? Basically push 8 1s and then just pop, increment, push until it's equal to 65, and then pop the thing before, push a 1, and it's a few lines of code. And the judge program is pretty straightforward, right? You just, each position, you figure out which squares it can intersect and see if that's anywhere else in the solution that you were asked to study. But the theme here is that we're doing a search. Okay, there's this collection of places where these queens could be placed, and we're trying to search that space. So let's look at another search problem. And that's a maze. So we're starting down here in the lower left, and our goal is to find a path that gets us out here at the upper right. And how do we run a maze typically? We take our finger and we start moving, and when we get to a decision point, we kind of keep our finger there, or maybe we just, eyeball it or something, and we start trying to find a different path. And if we get to a dead end, we come back to the last place we made a decision and we go somewhere different. And if we get to a dead end, we come back to the last decision and we try something different. And we keep doing that, and eventually, hopefully, we come out. But it may be that when I did all of that, I hit a dead end finally, and I have to come all the way back to here and say, okay, well, let's try going straight. And I'll come here and I'll say, okay, well, I can go to the right. Oh, that's a dead end. Okay, let's go this way, and so on. And we can make this systematic also using a stack. So what might this look like? Let's assign an ordering to our directions. So I'm going to just randomly pick an order of left, up, right, down. That's the order in which I'll try different paths. So I'm right here at the beginning. I can't go left, I can't go up, I can only go right. It's not really a decision point. Okay, so I start traveling down here. Here's a decision point. Okay, I'm going to call this point A. And I can either go up or I can go right. Okay, first thing I'm going to try is going up. So I'm going to go to my stack and I'm going to place the following information on my stack. I'm at position A and I'm trying to go up. Okay, now I just start going up and I have to turn left and I come to another decision point, so this is decision point B. And I can't go left, but I can go up, so I push onto my stack B going up. And I start going up, and here's another decision point, so I'll call that C, and I can't go left, but I can go up, so I'll push onto my stack. At C, I went up, and I keep going until I hit a dead end. What do I do at the dead end? I pop the top of my stack. I see that I was at position C, and I had tried to go up, so I say, okay, how about at position C, I go to the right? Can I do that? Yes. So I push a C and a right. And I follow it, and I come to a decision point D. So I can't go left, I can go up, so I'm going to say, okay, at D, I'm going up, and I go up, and I come over, and here's another decision point E. And I can't go left because that's the way I came. I can't go up because there's a wall. I can go to the right. So at E, I'm going to go to the right, and I do that, and I hit a dead end. What do I do at the dead end?
On top of stack.
Pop the top of the stack. Top of the stack was E, and I tried to go to the right. Okay, can I go down? I can, so I'm going to push E, goes down. And I'm going to keep doing this. And unfortunately with this order, this will actually get us to a solution eventually. But suppose that, suppose there was a wall right here. Okay. And I hit a dead end. Okay, well I popped the stack, which was E, going down. Down was my last option. That would tell me, once I get to E, there's no solution. So I'll pop the stack again. And I'll say, okay, at D, I went up. Let's try going to the right at D. And now I'll explore this path. I hit a dead end. I come back to D. I can't go down because that's the way I came from. So there's no solution there. So, so I pop off the D to the right. There's no solution there, so I go back to C. And I say, okay, at C, I went to the right. Can I go down? No, I can't. So you pop that off. And now you come back to B. And B, you went up. Okay, that didn't work. Can I go to the right? Yes, I can. So now I push B to the right, and I start exploring this. And again, this is very systematic. This will get you through all the possible pathways through the maze, and it's just a matter of noting if you get to the exit, and if you do, you're done. And if you exhaust all the possibilities, if you come all the way back to A, and you pop it, and you go to the right, and you follow all of this, and there's no solution, and you pop it, and you can't go down, so you try to pop again, but your stack is empty. That's it. There's no other paths.
Could it be possible to set this up for like a 3D maze going up and down as well?
Absolutely. Yeah, or higher. Right? As long as you can enumerate the possible directions you can make at each point, the possible decisions, you can store those in an appropriate structure, push them on a stack. You can also do this with a cube, but most of us use a stack. But as soon as we find that we've made a misstep, we could go back to the first decision that we made and make a different decision. But usually we do the last decision. That's just kind of a stack-based model of our thinking. Well, we can represent this pictorially as follows. So we started off at the beginning, and our first decision point was right here, and we said at position A we're going to try going up. So here's one possibility. At A we're going to go up. And we get to B, and B we can also go up. And we get to C, and C we can also go up. And that led us to a dead end. But at C we could also have gone to the right. So I'm not drawing this right. I'm trying to get fancy. So here's our first decision point, A. So we can go up, and that eventually gets us to B. And at that point, we can go up, and that eventually gets us to C. And at that point, we can go up, and that gets us to a dead end. But at C, we could also have gone to the right, and that gets us to a decision point, D. And at D, we could go up, and we can follow that over to E. And at E, we can go to the right, and that gets us to a dead end. Well, we can also go down, and that leads us somewhere. And if we fill out all the possibilities, at A, we could also go to the right. At B, we could also go right. C, we've got all the possibilities. But we can start designing this structure that looks kind of like an upside-down tree. Where we're starting here, we're going to call this the root. And we have these different options that we can follow. And it doesn't have to be binary. It could be that at some point we have 3 directions we can go. So maybe here we've got, point Q, and maybe we can go left or up or right. And there's other branch points that come up down there. But if we take this maze and we turn it into this tree-like structure, the question of running the maze becomes the question, how can we start from the root A and examine every possible path and ultimately find that somewhere there's a path leading to this exit node. Well, making this tree from this graph is very mechanical, right? As long as you have enough fingers to remember where you were each time you make a decision. That's what a stack does for us. And once you have this, actually you can start from the exit and just work your way back up and see immediately what the path is. And most mazes, if you try to solve them backwards, they're really, really easy. Right? If you start off here, you got to come down here and up here and over there and down there, and there's your entrance. And there's another direction that's hard. But if you put in the tree, right, you have 2 possibilities. Start at the exit and follow your way up, or somehow figure out how to visit every possible path along here. And we can do that using a stack. So starting next week, probably Monday or Tuesday, we're going to start talking about trees. And one of the first things we'll do with trees is traversal, this process of starting at the root and trying to visit every node, following every path throughout this tree. And again, it's a search problem. We're trying to search this space of, connections of lines to cover every possible combination. What we're also going to define is that this works. We're also going to find is that this works really well recursively. So here's your final thought. Suppose your goal is to figure out how to run this maze. You start looking at it and you get to position A, and you've got 2 possibilities. You can go up or you can go to the right. Okay, here's a way to do this without actually doing any work. I'm going to make 2 new mazes. I'm going to make one maze where I block off this path on top. and I get rid of this, and I pretend I'm starting right here, and my only option is go to the right. I'm going to hand this to a friend and say, can you solve this maze for me? And they'll come up with a solution, or they'll say there's no solution. Okay, if they tell me there's no solution, I'm going to go to my original maze, and I'm going to block off this option. I'm going to get rid of this wall and hand this to another friend and say, can you solve this for me? And they'll say, yeah, go up here, and they'll give me a solution. I'll take that, superimpose it on here, and say, oh, I solved your maze. Go down here, turn left, and then do what my friend did. Did I actually do any work myself? Not really. I took two possibilities, found two friends who could solve a slightly simpler maze, and then took the one that had a solution and said, okay, just turn left and then do their solution. Now, how did my friends solve the maze that was slightly simpler? Exactly the same way. They got to this decision point and they blocked off this wall, handed it to a friend, blocked off that wall, handed it to another friend. The friend that got this maze gave them a solution, and they said, okay, when you get here, go straight. And they handed that back to me. Nobody's ever really doing a whole lot of work. And in the end, you know, somebody got a maze that basically said, okay, you're going to start right here. Can you get out? And they said, yeah, just go straight, take a right, take a left. So the only person who actually solved the maze from start to finish had a simple maze with no turns in it. So that's recursion, okay? That's what we're going to be doing for the next few weeks. That's what we just finished in 215 this quarter. And it's a kind of magical way to write this code where we really don't need to do a whole lot of work, which is kind of nice. All right, so we'll jump into trees next week, and we'll have a good time with that. All right, I will see you then. You can still